In this video, I'll cover transformations of sine. Before I jump into some examples of transformation of sine, I want to refer back to the unit circle. So I have this unit circle, and when we talk about a unit circle, what we're referring to is a circle with a radius of 1. So this length right here is 1. Now let's consider that we always start at the initial side. This is the positive x-axis, and we're going to rotate around counterclockwise. So we have some theta here, and we are going to terminate at some coordinates. So we have our initial side, we rotate theta degrees, and then we have some point here of x and y. Now for our right triangle, this leg here is our x value, and this leg here is our y value. Now let's look at this coordinates of x, y in terms of trigonometric ratios. So from this angle right here of angle theta, then cosine of that theta, which by definition is adjacent over hypotenuse, and the hypotenuse for our unit circle, our radius, is 1. So that's going to be x over 1. So we can see then that for cosine theta for a unit circle is equal to x. So we can refer to this particular point in terms of trigonometric ratios as cosine theta, comma, and then some corresponding y value. Let's consider sine of theta, which is defined by opposite over hypotenuse. From this angle here, opposite is y over hypotenuse 1, so I have y over 1. So we can see that for sine of theta, for a unit circle, sine of theta equals y. So in terms of trigonometric ratios, this coordinates of x, y can be represented by cosine theta, sine theta. So let's do a rotation. So if we don't rotate at all, so our angle is 0, then this particular point here is 1, 0. If we rotate 90 degrees, then this particular point here is going to be 0, 1. If we rotate 180 degrees, this point here is going to be negative 1, 0. At 270 degrees, we have a point at 0, negative 1. And then at 360 degrees, we're back to this point here of 1, 0. Now I'm going to be graphing sine of x, and sine of x is going to be, we'll just be looking at the y values. So when sine of x, when we have sine of 0 degrees, then our y value is 0. So sine of 0 degrees is 0. For sine of 90 degrees, our y value is 1. Sine of 180 degrees, our y value is 0. Sine of 270 degrees, our y value is negative 1. And sine of 360 degrees, our y value is 0. So we end up with a graph that looks something like this. Now this graph doesn't really have a starting and ending point, so I'm going to indicate that this graph continues with these arrows. So I like to think of a periodic function. This is a sine function or a periodic function, and I like to think of these periodic functions like you would weather, and I should say seasons. So we start here at when our angle is 0 degrees, we start at springtime, followed by a maximum, summertime, followed by an inflection point, which would be our fall, followed by the minimum point, which would be our winter, and then we're back to springtime again. All right, let's look at our next graph here. I have y equals sine of x plus 3. Now I'm adding something to our function. Our function is sine of x, and I'm adding something to the function. So to the function. Whenever we add or do something to the function, then the move is it will be in regard to the x-axis. The move will be in regard to the x-axis. So we're going to be moving away from the x-axis by a positive 3 units. So we have 1, 2, 3. So this is what we call this line here is the principal axis. What used to be the x-axis, we call this the principal axis because the graph oscillates across this line. What used to be the x-axis, our principal axis used to be the x-axis, has now been shifted up 3 units along with all of the other points. So we start at springtime, or this inflection point, and then we reach a maximum, and then we have our inflection point again, followed by a minimum, and then we're back to our inflection, our period. We're right on the principal axis again. So our graph is going to look like this. And it will keep on oscillating forever, so I'll indicate that with our arrows. Here I'm doing something in the function. Instead of to the function, I'm adding something or subtracting something in the function. So in the function. And when I do something in the function, the move is in regard to the y-axis. So we're going to move from this y-axis here. And we're going to move by 90 units. Now it seems like because this is negative 90, it seems like this should be a shift to the left, but in fact it's a shift to the right. So we're going to be, and the way that I justify this to my students is that we're not looking at the negative 90, we're asking ourselves, what does this x have to be so that in parentheses, this goes to 0? And the answer is 90, or positive 90. So I'm going to shift what used to be springtime, or this inflection point here, is going to be shifted all the way over to 90 right here. And this summertime, or this maximum point that was at 90 degrees, is now going to be over at 180 degrees. So all the points are going to be shifted over to the right by this 90 degrees. So that means I'm going to, at this point, we are going to go from springtime to summertime to fall to wintertime. And again, this graph it doesn't really have a starting or ending point. It will just continue on forever. So I'll indicate that with arrows. Next one here, I am multiplying a 3 to the function. So to the function. Because I'm adding something to the function, then the move is in regard, it will be a move in regard to the x-axis. So the move is to the x-axis. So in this case, this is our amplitude, this is our wavelength, how high the wave is. And so our wave is, instead of 1, in fact, you can just imagine that in front of here, there's an implied 1. Here we have a 3, so instead of a wave of 1, we have a wave with a size of 3. So we're going to go all the way up to 3 and all the way down to negative 3. So we measure the height of a wave from the principal axis, and the principal axis in this case is the x-axis. So we started our inflection point, we still hit our maximum and minimum points for the same degree. So that should look something like this. So it's very similar to our graph that we have, our first graph that we did here, except for our wavelength is now 3 units instead of 1 unit. All right, let's look at this one. So here we are multiplying by a negative 1. So this is, we're multiplying to the function. This is to the function. And we're multiplying to the function, so this is in regard, the move is in regard to the x-axis. And in fact, this is a reflection across the x-axis. So what used to be with our graph, our y equals sine of x, would look something like this. We have reflected across the x-axis, so the graph is going to look something like this. All right, let's look at the next one. If it was a negative in the function, it would be in regard to the y-axis, so it would be a reflection. In fact, I think I have that one next. In fact, I'll just jump down to that one next since we're talking about it. So we're doing something, I'm multiplying by a negative in the function, so this is in the function. So the move is in regard to the y-axis, so we are reflecting across the y-axis here. So this piece of the graph right here has now been reflected here. And this piece right here has been reflected here. Well, you can look at this and say, well, this looks really the same as what we just did. And it does look the same if we have a negative in the function and a negative outside of the function, when we're multiplying a -1 in the function versus to the function, it feels the same, but it's only because of the symmetry of this graph. If we looked at a different graph that wasn't symmetrical across the origin, it would be more obvious that doing something in the function would be a reflection across the y-axis, whereas when we multiply a negative to the function, it's a reflection across the x-axis. Let's look at the next one here. We have sine of 2x. Well, this 2, it influences the period. So this influences the period. And the period is, well, our equation would be b equals 360 over p, or p equals 360 over b. Now in this case, we have our b value. We call this our b value, and I'll talk about why it's our b value in just a moment. Then we can take this 2 and we plug it in here, and we have 360 divided by 2. That gives us a period. In this case, if I have a period of 360 divided by 2, that gives me a period of 180. That means instead of having a period that repeats itself every 360 degrees, I'm going to repeat every 180 degrees. So I need to go from springtime to summertime to fall to wintertime and back to springtime after 180 degree rotation. So that would mean that we're looking at something like this. So we're going to go up, we're going to go back down, we're going to go back all the way back down to our minimum and then back up. And of course this graph, it repeats itself, so we're going to, looks like, we're going to have something like this that will just repeat itself forever. All right, so let's look at the last one, and I do want to talk about what this b value means here. So here we have y equals sine, 3 times sine of 1/2 times the quantity of x plus 45 minus 6. So I have y equals a times sine of b times x minus c plus d. Now this a, it represents my amplitude, or my wave height. This b value, this is my influences the period. And our equation is b equals 2 pi, let's not use radians, 360 over p, or p equals 360 over b. The c, this is my horizontal shift. And the d is my vertical shift. This looks very sloppy. But anyway, let's go ahead and graph this. So I need to, my principal axis is going to drop by -6, or it'll drop by 6. So here we have 1, 2, 3, 4, 5, 6. My principal axis is here. It looks like my wave is 3 units up, so 1, 2, 3. So we're going to go this high. The wave will also drop below the principal axis by 3 units, so we'll be going down this far as well. we have since we have our vertical shift, we've shifted down. This is my x-axis right here, right? So this is my, we're going to start somewhere on this line because this is sine of x. And we also, it looks like we have a horizontal shift of 45. So this would be, this is our 90 and 180 and 270. Because it's x plus 45, it means that we're going to shift to the left. So if this is negative 90, then negative 45 would be here, which means that we're going to start our graph at this particular point, where the principal axis and our horizontal shift, where they come together, that's where our starting point is. Now, there is no reflection, so I'm going to start, this will be my springtime, or my inflection point where I start to go back up. So I'll be going all the way up and all the way back down, starting at this particular point. Now, it does matter, this period here of 1/2, that is relevant, so our period equals 360 degrees over 1/2. Well, 360 is the same thing as 360 over 1. Over 1/2, when we have a fraction divided by a fraction, we multiply, so that's going to give us what, 720? So 720, which means that by 360, we will only have a half of a period. So that means that we're going to start here, and instead of having a full rotation, which would have been here, right, because of we're subtracting 45 degrees. So 360 minus 45, that's where one period would have ended. But because our period has been doubled in size, at this point we only have half of the period. Instead of going all the way up, all the way back down, and all the way back up, which would be a full period, we only have, in this 360 degrees, we only have half of the period because our period is 720. So that means then that this is going to be our maximum. So 180 minus 45 would give us our maximum point. So we have something that's going to look like this. And it looks a little sloppy, but you know, that's the idea. Anyway, I hope this video was helpful, and I hope you have a wonderful day.